Hello guys, welcome to my YouTube channel Physics Prince. My name is Deepak. I'm going to teach you all 9 subjects of physical science in detail. My courses are absolutely free of charges. My courses are going to help the students who are preparing for CSIR, NET, GATE, NT exam, PhD exam, SET exam, IIT-Jam, Jest, Tifr and other exams related to physical science. Okay, so this is the first lecture of thermodynamics and statistical physics. Okay, and also guys, I would request the students who haven't subscribed my channel yet, please subscribe my channel and watch my free live lectures which are going to help you to crack the exams related to physical science. Okay, so let's get started guys. So we are going to start thermodynamics and statistical physics. Okay, first we'll start with thermodynamics. Okay, well, so first thermal equilibrium. Okay, thermal equilibrium. Thermal equilibrium. Thermal equilibrium. Thermal equilibrium. In thermal equilibrium, we know very simple thing. We have already studied in class 11, 12, BSc, MSc, right? Thermal equilibrium, in thermal equilibrium, we know that is temperature T1 equal to temperature T2, right? Second is mechanical equilibrium. Second point is mechanical equilibrium. Mechanical equilibrium means the pressure will be same, P1 equal to P2. Okay. Third point is that is chemical equilibrium. Chemical equilibrium. Chemical equilibrium means that is mu1 equal to mu2. That is chemical potential. Okay. Mu is chemical potential. Chemical potential of first system equal to chemical potential of second system, right? So this is mu is chemical potential. Okay, and T1, T2 we know the temperatures, and P1, P2 are pressures. Okay, so now we'll study that is thermodynamical equilibrium. Okay, thermodynamical equilibrium. Thermodynamical equilibrium. Uh, thermodynamical equilibrium, right? When the when when the system is in thermal equilibrium, mechanical equilibrium and chemical equilibrium, okay, in that case the system is known as is in thermal equilibrium. Okay, so thermal equilibrium means when T1 equal to T2, okay, system will be called in thermodynamical equilibrium when T1 equal to T2 and P1 equal to P2, P1 equal to P2 and mu1 equal to mu2. Okay, if these conditions are satisfied, then the system is called that is in thermodynamical equilibrium. Okay, thermodynamical equilibrium system is in thermodynamical equilibrium means when the temperature T1 equal to T2, pressure P1 equal to P2 and mu1 equal to mu2, right? And in that case system is called in thermodynamical equilibrium. Okay, very simple points. Okay, now next is, we know these are very simple points guys. Okay, ideal gas equation we know, right? That is ideal gas equation. Ideal gas equation. Okay, ideal gas equation is PV equal to nRT, right, where P is very important. Okay, we'll use it. P is pressure of the system. I'll write here. P is pressure of the system. Okay, V volume of the system. R is gas constant. And N equal to number of moles. Number of moles. Okay, so this is the ideal gas equation. PV equal to RT. P is the pressure, V is the volume of system, R is gas constant, and N is number of moles. Okay. Okay, this is the one. Now different type of system we are going to study. Okay, now the first system is isolated system. Okay, isolated system. Okay, so isolated system means this one. I'll make it. Okay, this is any system. Okay, when there is no exchange of heat between system and surrounding. Okay, so that is called isolated system. Okay, NVE. Okay, NVE. N is number of moles, V is the volume, E is the energy of system. Okay, so number of particle. Okay, so this is the isolated system, guys, because there is no exchange of heat between system and surrounding. Okay, so this is called isolated system. Okay, so temperature and volume and energy will be same. Okay, so this will not change. Okay, so no transfer of heat energy between the system and surrounding. Okay, so this is the isolated system. And for example, like thermal water bottle. Okay, thermal water bottle. Thermal water bottle. Thermal water bottle. Okay, thermal water bottle. Okay, thermal water bottle. So when in thermal water bottle, you can see there's a rigid walls. Okay, so there is no heat transfer between system and surrounding. Okay, so rigid walls. Rigid walls. Number 2, that is non-conducting walls. Non-conducting walls means adapic. Non-conducting means there is no transfer of heat between system and surrounding. Non-conducting is also called adiabatic. Okay, adiabatic. I was just checking the camera. Okay, so also there is no exchange of that is material. Okay, so that is impermeable walls. Okay, no exchange of this material of the system. Okay, so that is impermeable walls. This is the isolated system, guys. For example is thermal water bottle, right? The walls are rigid, non-conducting walls, that is adiabatic walls, means there is no transfer of heat energy between system and surrounding, and impermeable walls means that gas will not transfer into the surrounding. Okay, so impermeable wall, okay, will not allow to the wall which will not allow to penetrate the gas from it. Okay, so that is impermeable walls. Well, now closed system, different type of system we are studying, that is closed system. Closed system. Closed system. Closed system. Okay. Closed system. Closed system means that no transfer of material, only energy can transfer. Okay. In isolated, there is no transfer of no transfer of material no transfer of material, only energy or heat. Okay, only energy can be transferred. Energy. Okay, no transfer of material, only energy can transfer. Okay, so and second point of it, this is walls are impermeable. Walls are impermeable. Okay, walls are impermeable, conducting. Okay, conducting. Walls are impermeable means material cannot transfer, or the wall will not allow material to transfer from it. Okay, and conducting means it will allow, or diathermic means it will allow energy to transfer, and there is a transfer between system and surrounding, energy transfer between system and surrounding wall. Okay, conducting walls, and this wall will be rigid. Okay, this will be rigid as well, can be exchanged, energy can be exchanged, both can be exchanged. Okay, and like for example grand canonical. Okay, example is grand canonical ensemble. Okay, grand canonical ensemble. We'll study ensemble as well in statistical physics. Okay, so this will go when we complete thermodynamics, then we'll start statistical physics in the same series. Okay, so grand canonical ensemble is the example. Okay, well, so this is about the different types of system. Now degree of freedom, so we are going to study degree of freedom. Okay, degree of freedom. Degree of freedom. Degree of freedom. Degree of freedom, so we know that degree of freedom definition, the minimum number of coordinates, required to define, minimum number of coordinates required to define motion. Okay, so minimum number of coordinates required to define motion of particle or motion. Okay, that is called degree of freedom. Okay, so there are three types of degree of freedom. Okay, so this is that is translational, translational degree of freedom. In short, I am writing DOF. Okay, DOF, degree of freedom. Okay, so translational degree of second is rotational degree of freedom. Rotational degree of freedom, and third is vibrational degree of freedom. Vibrational degree of freedom. Okay, vibrational degree of freedom will be at high temperature. Okay, at high temperature. At high temperature. Okay, vibrational degree of freedom at which will be at high temperature. Okay, so here also I would like, there are 2 points which you also need to know. Okay, temperature T will be constant. Okay, constant, T will be constant. When only for purging, it means T will be constant. Okay, T will be constant when heat heat energy is exchanged. Okay, T will be constant when heat energy is exchanged. That time T will be constant, guys. Okay, very important. That means we will, when we will be constant, when particle is transferred. Okay, when material is exchanged, or you can say material is exchanged, or when particles are transferred, or when particle okay, now we'll study different type of degree of freedom. Okay, for monoatomic, first is for monoatomic gas. Okay, monoatomic monoatomic gas, monoatomic gas. Okay, monoatomic gas, monoatomic gas, for example, what are the monoatomic gas? That is helium, neon, argon, etc. Okay, helium, neon, argon, etc. These are monoatomic gas, helium, neon, argon, etc. Okay, so for a monoatomic gas, for 3D, degree of freedom will find. Okay, so this is y-axis, this is x-axis, and this is z-axis. Okay, so for monoatomic gas, in case of 3D, degree of freedom DOF is 3. Okay, so we can write like in 3D, the degree of freedom F is 3 for monoatomic. Okay, x, y, z coordinate, we need 3 coordinate system to explain the monoatomic gas. Okay, so degree of, in 3D, the degree of freedom for monoatomic gas is 3. Second, in case of 2D, the degree of freedom is 2. Okay, so in 2D we need two coordinate system to describe the motion of particle. Okay, number third, in if we talk about 1D, that implies degree of freedom is 1. Degree of freedom we can write by F. Okay, next, this is the case of monoatomic gas. Okay, next is diatomic molecule. We're talking about diatomic molecule. Diatomic diatomic molecule. Diatomic molecules. Diatomic molecules. Diatomic molecules, which are this O2, this is oxygen, right? Nitrogen, N2, and H2, hydrogen, etc. Okay, so these are diatomic molecules, guys. Okay, so for this one is like this. this is y-axis, this is z-axis, this my apology, this is z-axis and this is x-axis, guys. Okay, this is x-axis. Okay, so for diatomic molecules, so there are the 3 degree of freedom, right? Translational, rotational, and vibrational. Okay, so translational DOF is 3. Okay, for diatomic molecule, and rotational degree of freedom is 2. Okay, so for diatomic molecule, so at normal temperature, normal at normal temperature, degree of freedom F for diatomic molecule is 3 plus 2. 3 for translation, this is 3 is translational degree of freedom plus rotational degree of freedom, 2 rotational degree of freedom means 5. At normal temperature for diatomic molecule, degree of freedom is 5. Okay, and now at high temperature, degree of freedom is 7. Degree of freedom is 7. 3 plus 2 plus 3 plus 2 plus 2 equal to 7, because at high temperature there will be vibrational degree of freedom, and that will be 2. Okay, so 2 plus 2 plus 2. This is translational degree of freedom, this is rotational, and this is vibrational. Okay, at high temperature, because vibrational degree of freedom will also be get added. Okay, so 7, very important thing. Okay, you need to note down. Next I'll give one example. Okay, so as a question I'm taking for 2D case. Okay, example for 2D. Okay, in 2D, right, if you talk about 2D, this is molecule, guys, and we have in case of 2D, we have just what we have done is we have restricted this in 2D only 2-dimensional, right? For that, motion translation degree of freedom is going to be translational DOF is going to be 2, and rotational is going to be rotational DOF is going to be 1, because so we have restricted this in only 2D, right? If we talk about 3D, in 3D mono, it's these this is the case of 3D, guys. Okay, in 3D we are talking about, these are in 3D. Okay, in 3D, so degree of freedom is at normal temperature, degree of freedom is 5. Okay, but if we talk about 2D, right, the translation degree here in 3D, translational degree of freedom is 3, rotational is 2 at normal temperature. So here at normal temperature, translation degree of freedom are going to be 2 because it's 2D, and rotational is going to be only 1, right? So DOF, that is F, is going to be 2 plus 1, that is 3. Okay, so degree of freedom is 3 in case of 2D. Okay, this is because of translational. 2 are translation degree of freedom and 1 is rotational degree of freedom. I hope, guys, you have understood it. Next point. Okay, Abhi, you are asking, like, okay, yes, Abhay, I'm taking all 4 lectures every day, right? First lecture, all are live lectures. First lecture, in first lecture, I'm solving PYQs. Okay, PYQs of that November 2020 PYQs. Okay, so you can check my playlist, Abhay. You can see that I have completed quantum mechanics, in 29 lectures, complete detailed course of quantum mechanics. That was also live, so you can check in my playlist. And I have completed mathematical physics in 35 lectures. Okay, and that is also complete detailed complete course of mathematical physics, right? I have completed that is 2019 paper of June and December both in 11 and 10 lectures respectively. You can check. I have completed seven that I have completed optics in a detailed course of optics in 7 lectures. You can all and also I have completed that 8 lecture. There is 8 lectures of quantum mechanics PYQs also there. 2 lectures of mathematical physics PYQs. So I would request you, Abhay, to please check my playlist. Okay, there you will get all detailed courses. And nowadays I'm taking 4 live classes every day. Two classes for this thermodynamics and electronics, and 1 class is for that was for solid state physics, that is condensed matter physics. Okay, and also I'm solving 2022 papers. At the moment I'm solving part C questions, so part B questions are completed, right? So after completion of 2022 paper, I will solve 2021, then 2022, then 2023. Okay, so you can check those courses, guys, courses away. And this is the live lecture of uh, thermodynamics. Okay, thermodynamics and statistical physics. Okay, so this is the degree of freedom, and this is 3. Okay, for the 2D. Well, next is so if we talk about triatomic molecule, triatomic molecule. Triatomic molecule. Triatomic molecule. So we have already studied diatomic molecules. Okay, degree of freedom. Now degree of freedom for triatomic molecule. I will talk about 3D first. Okay, so triatomic molecules. For triatomic molecules, this is triatomic molecules is divided into 2 parts, guys. Okay, so there are 2 types of triatomic molecule. One is linear and the second is non-linear. Okay, so this is linear and this is non-linear. This is linear and this is non-linear. So linear atom is like this. Okay, and non-linear is this. Okay, this is linear and this is non-linear. Okay, so for triatomic molecules are of 2 types, linear and non-linear. So this is the linear molecule and this is the non-linear molecule. Okay, and for this degree of freedom is there is a formula, guys, you need to note down. This is 3n minus k. So degree of freedom F equal to, very important formula, you need to note down. Okay, so this is F equal to 3n minus k. Okay, so where n is number of atoms. In triatomic case, the number of atoms are 3. Okay, number of atoms, and k is number of number of constraints. Okay, constraints k is number of constraints. Okay, so n is number of atoms and k is number of constraints. So you can easily find out the degree of freedom. Okay, so now we'll find degree of freedom for linear molecule. Okay, DOF for linear molecule. degree of freedom for linear molecule. Okay, so linear molecule is linear triatomic molecule, this one. Okay, well, so F, we have a formula, right? 3n minus k, 3n minus k, that is F equal to 3n minus k. Since n equal to 3, we know, right? N equal to 3, because it's a triatomic molecule, and n is the number of molecule I have already explained, or and k is the constraints, right? Restrictions or a number of constraints. So for in case of this linear molecule, linear triatomic molecule, k is 2. Okay, so k is 2. So this means F is going to be 3 into 3 minus 2, right? So this is 3 3 is 9 minus 2, that is 7. Okay, so this is at normal temperature, guys, at normal temperature. Okay, this is at normal temperature. Now second is degree of freedom. Okay, so at high temperature, okay, so this is at normal temperature. Now non-linear molecule. Okay, next is DOF, degree of freedom for non-linear, degree of freedom for non-linear molecule, degree of freedom for non-linear molecule. Okay, so this is since n equal to 3, and for this, okay, and it's a triatomic, right? And k equal to 3 for non-linear molecule. Okay, k will be 3, restriction will be 3. So F is going to be, F equal to, we know the formula, 3n minus k, right? So F is going to be, this is the formula, right? Okay, 3 into 3 minus 3, this is 9 minus 3, that is 6 at high temperature. Okay, now monoatomic. Okay, so this is the formula you need to know. Now this is, so if we can also use this formula, that is F equal to 3n minus k for monoatomic also. Okay, mono, this is applicable for mono, di and tri. Okay, monoatomic. For monoatomic, n equal to 1 and k equal to 0, guys. Okay, so F is going to be, that's we have already found, right? K is going 3 into 1 minus 0, that is 3. Degree of freedom is 3 for F, I have already explained, right? So we can use this formula and we can also get it for monoatomic as well. Okay, and for diatomic as well, right? For diatomic, for diatomic, n equal to 2, right? There are two atoms and k is 1. K is 1, so F is going to be 3 into 2 minus 1, so this is 5. These are at normal temperature. Okay, simple things, right? So this is for diatomic. Now for polyatomic molecule, right? For polyatomic molecule, poly polyatomic molecule, for polyatomic polyatomic molecule, we know that is n greater equal to 3, right? N will be 4, 5, 6, 7, right? Polyatomic molecule, the n is greater than 3, so F is going to be, for polyatomic molecule where n is greater than 3, the formula is going to be Nd minus k, where n is number of molecule. Okay, where n is number of molecule number of molecule, and K is, and D is dimension, guys. D is dimension. Okay, D equal to dimension. D equal to dimension. Okay, D equal to dimension, and so you can easily find out. So like suppose uh, n equal to 4, right? And in 3D you need to find out. So this is 3 into 4, 1. Vibrational. So this is the vibrational degree of freedom. Okay, vibrational degree of freedom. Vibrational degree of freedom for linear molecule. This is triatomic we are talking about. Okay, linear and non-linear. Linear and non-linear. So for this, F is going to be 3n minus 5. Okay, vibrational degree of freedom. Okay, and F is going to be for this 3n minus 6. Okay, this is for this formula is vibrational degree of freedom for linear and non-linear molecule. Okay, and here we have studied this one. So degree of freedom for non-linear molecule, right? Degree of freedom for linear molecule and non-linear molecule, right? If you talk about vibrational degree of freedom, then 3n minus 5 and 3n minus 6 for non-linear and 3n minus 5 for linear. Okay, well guys, I'll stop here, right? In remaining we'll do in next class. Okay, and also guys, I would request the students who haven't subscribed my channel yet, please subscribe my channel and watch my free live lectures which are going to help you to crack the exams related to physical science. Okay, okay guys, thank you so much. Bye now.